Okay, so the next problem we want to look at is median selection, which is really one of those fun problems because it's a simple problem to state, and there are two algorithms that are very natural. One of them is very natural for this problem, and it's very fast in practice. And we have another algorithm which is, in fact, slightly slower in practice, but still is, it's deterministic, so it always have a fast running time. And there are some nice ideas involved in both algorithms. So with no further ado, the input is an unsorted array of numbers. If you want, you can think about it as just an unsorted list. We don't really need here the array property. We just need to be able to access the number, even sequentially, like in a list. And we would like to return the the number that is of certain rank in the array. So what is the rank of a number? You take the array and you sort the numbers. Let's assume that all the numbers are distinct, so we don't have to deal with nonsense. And the number of rank j is the jth smallest number written in the array. Namely, in the sorted array, the jth number is the number written in the jth entry. Okay? So median selection or selection asks the following question. I give you the numbers. Can you compute the jth number, the number of rank j, among this set of n numbers? Okay, and usually we're interested in the middle element called the median, right? And now you might ask, why do we care about the median? So, for statistics reasons, right? We have a bunch of numbers. Some of them might be outliers, too small, too large. So we want to kind of, we have since it's a large set of numbers, we want to summarize the set with one number. So the median is a good summary. It says, well, the middle of those numbers is this value, right? And this middle is not affected by how much the extreme right and the extreme left of the numbers are small or large. Okay. So, as I mentioned earlier, we are going to assume that all the numbers are distinct. Okay, so I already described the first algorithm. You just sort the number and you output the jth number. That's how I define the number of rank j. So selection would take off n log n time. And the question, of course, is that do we really need to sort, right? And if you think about it, we don't always need to sort, right? If I want the smallest number, j equal 1, then I can just count the number and compute the minimum number. So that's easy. If j is equal to 2, well, it's kind of a bit more tedious. So you can keep track of the two smallest number encountered and, scan the array and find the jth number. Or a more natural algorithm is, in fact, to do the following. You take the array, you find the minimum number, right? Let's assume this number. You write it in your array, then you delete it from the array, and now you find the smallest number in the array without this number. This is the second smallest number, and you repeat this process, right? Finding the smallest number takes off n time. You want the jth number, so this would take off j n time. And if j is small, this is a good algorithm, right? If j is something like log n, well, if j is 10, then this is hopefully faster than sorting the numbers, right? But this is still not very satisfying because the running time is jn, and in particular for the median, where j is equal to n over 2, this is just quadratic time, right? So this is a simple algorithm, but it works only if the value of j is really, really small, and that's not very interesting. So the question is, can we do better for all values of j? And the answer is yes, and how to do it, we will see next.